When we look at the landscape of machine learning, most algorithms are built to evaluate isolated moments in time. But down in the deep learning tier, recurrent neural networks operate on a completely different dimension. They are designed to process sequential data. Curious, in sequential data, a single piece of information means very little on its own. Meaning is derived entirely from the order the data arrives. Standard feed-forward networks struggle with this. They suffer from a structural amnesia. They process an input, spit out a prediction, and immediately wipe their memory blank before the next input arrives. If you are analyzing a static photo, amnesia is fine. But if you are analyzing a spoken sentence, a shifting stock price, or a moving vehicle, you have to engineer a network that possesses a continuous sense of time. Recognizing isolated patterns is a starting point, but to interact with the real world, an artificial intelligence requires the memory of the past to accurately anticipate the future. The path to that memory began in 1990, when cognitive scientist Jeffrey Elman set out to test how an algorithm might learn the structure of time. Elman fed a neural network a continuous stream of simple sentences, word by word. He gave the network no labels, no vocabulary lists, and no rules about human grammar. He simply asked the network to guess the next word in the sequence. By analyzing the accuracy of those predictions, he discovered that the network had spontaneously clustered words into distinct noun and verb categories. Revealing the mechanism making this possible was a set of context units. At every step, the network saved a copy of its own internal state and referenced it alongside the next word. Elman proved that a sequence works in a way a collection never can. Structure lives in the order of the data, and contextual memory is an absolute architectural requirement for understanding it. Today's recurrent neural networks take Elman's context units and build their entire architecture around a continuous feedback loop. As data flows through the loop, the network maintains what is called the hidden state. This is a memory vector, a dense mathematical summary of everything the network has seen up to the current moment. Standard networks move linearly from input to output. An RNN, however, reuses the exact same computational cell for every single step in time. When a new piece of data arrives, the cell performs its calculation, updates the hidden state, and passes that state forward to itself, like a runner passing a baton in a relay race. This looping mechanism cures the amnesia problem. It stitches isolated data points into a cohesive, readable timeline. To see how a sequence is actually processed, we refer to this unrolled diagram. The transformation arrow shows how the single looped cell on the left stretches out into a horizontal, multi-step sequence on the right. At time step 1, the network ingests the, initializing a blank hidden state. At step 2, it receives cat, merging it with the purple memory arrow carrying the previous hidden state. Note the bottom right. The exact same shared weight matrices apply across the entire sequence. Unrolling the loop reveals the structural reality of the RNN. It turns the invisible dimension of time into a physical, calculable chain. Inside the cell, past context and current word vectors are multiplied by weights and summed. This passes through a tanh function, squashing values to prevent runaway calculations. The output splits, generating an immediate prediction above, while routing updated memory back for the next step. That tight sequence of addition and squashing is the literal mathematical engine of artificial memory. The unrolled chain provides a continuous flow of context, but this structure has a technical limit when sequences get too long. This chart maps out a phenomenon known as the vanishing gradient. During training, the network tries to correct its errors by sending a mathematical signal backward through the chain. Over many steps, that signal decays towards zero. The practical consequence is noted right here in the center. If the word clouds appears at the start of a sequence, the network often fails to link it to the word rain, appearing just 20 steps later. This specific limitation forced the development of next-generation algorithms. Researchers engineered more complex, gated architectures, like LSTMs and GRUs, specifically to protect the memory signal across longer intervals. Despite these limits, the feedback loop introduced the concept of stateful processing to deep learning. It showed that a network could go beyond recognizing static patterns and start capturing the structural relationships that exist within a sequence of data. Now, let's open up the code notebook. To see how a recurrent neural network processes sequential data, we are going to look at the exact Keras implementation from Chapter 10 of 50 Algorithms Every Programmer Should Know. The task here is sentiment analysis. The network reads an entire movie review, one word at a time, and condenses that sequence into a single prediction. Is the review positive or negative? Translating the theoretical concept of a memory loop into a functional Python script clarifies exactly how a neural network handles the dimension of time. Neural networks cannot read raw English text. Before the first input even enters the model, the dataset converts every word into a unique integer ID based on its frequency. To keep the data manageable, the code applies a strict limit. Setting the vocabulary size to 50,000 filters out the rarest words, retaining only the most common tokens the model actually needs to recognize. Because reviews naturally vary in length, we use the pad sequences function. This forces every single review to be exactly 500 steps long by filling in any empty space with zeros. This uniform length is a strict requirement. The neural network needs standardized batches to successfully carry its hidden state forward from step 1 all the way to step 500. Inside the sequential model, the first layer is the embedding. It takes the raw integer IDs and expands them into dense 50-dimensional vectors, creating the true mathematical input for each time step. A dropout layer follows, randomly silencing 25% of the signal during training to force the network to learn robust patterns instead of memorizing the training data. Then we reach the single line of code that constructs the 500-step recurrent memory loop. This diagram shows why the author chose an LSTM layer over a basic RNN cell. The LSTM solves this using internal gates. Finally, a dense layer applies a sigmoid activation function. It takes the final hidden state produced at step 500 and compresses it down into a single probability score between 0 and 1. The massive mathematical complexity of a recurrent memory system is completely hidden behind just a few lines of Keras architecture. The model compiles using binary cross-entropy to calculate the error and relies on the atom optimizer to update the weights over 3 epochs. Because we are dealing with sequential data, training requires backpropagation through time. The algorithm calculates the prediction error at the sequence's end, and the gradient flows backward horizontally through every preceding time step. Even though the chain unrolls across 500 distinct steps, this entire backward flow serves to update only one single shared set of weights. Backpropagation through time acts as the engine that forces the shared weights to learn dependencies from the past. Stripping away the surrounding code reveals how little syntax is required to deploy a temporal memory system. The true challenge lies in recognizing when a sequence length dictates an upgrade from a plain recurrent cell to a gated LSTM to protect early signals. Architectural mastery means understanding the capacity of a recurrent loop to capture time, and the vulnerability of that same loop to long-range amnesia. This high-level grid categorizes algorithm number 38, the Recurrent Neural Network, or RNN, within the broader landscape of deep learning and computer science. If you scramble the sequence, you destroy the data's logic. This diagram shows an unrolled sequence processing the phrase, "the cat sat on." It illustrates the most common real-world application, language modeling. Your smartphone uses an RNN to carry the context of previous words forward to identify the next logical step. We can also run this process in a many-to-one setup. In sentiment analysis, an RNN ingests an entire paragraph of text, step by step, building a continuous understanding of the tone before outputting a single final verdict, positive or negative. The architectural engine making all of this possible is called the hidden state. It is the specific mechanical solution required to maintain context across any ordered data stream. That stream can take many forms. If you hold an entire sequence of English words in memory first, you can process them together and output a translated sequence in French. The data doesn't have to be text. An RNN can step through the peaks and valleys of an audio waveform for speech recognition, or track the specific sequence of pen strokes on a tablet to analyze handwriting. In the stock market or weather forecasting, we look at time series data. Here, the network relies on the historical trail of data points to project the next likely value into the future. Wherever time, physical order, or logic creates a sequence, the RNN provides the continuity required to read it, efficiently compressing complex relationships. This gives the network what we call order awareness. An older bag-of-words model treats the words not and good as isolated concepts that just happen to be present. An RNN locks those tokens into a directional chain, recognizing that not directly precedes and modifies good. The elegance of the RNN lies in this ability to handle infinite temporal flexibility while relying on a very small, efficient set of parameters. By step 20, the network has often forgotten step 1. Variations like LSTMs and GRUs were built to solve this memory issue. However, even those upgraded models couldn't fix the architecture's inherent hardware bottleneck. By design, an RNN processes step 2 only after it finishes step 1. A modern GPU has thousands of cores designed to execute tasks simultaneously, but the RNN forces those cores into a single file line. Most of your hardware sits idle. When training on billions of words, this one-step-at-a-time approach makes the process practically impossible for massive modern datasets. This is why the industry shifted to the transformer architecture. Transformers look at every word in a sequence simultaneously, utilizing every core in a GPU and cutting training times from weeks to days. Ultimately, the plain RNN was sidelined by its own sequential design. It simply could not scale alongside the massive parallel processing power of modern hardware. Despite these limits, the plain RNN remains a specialized tool for short to moderate sequences, where the data relies on strict step-by-step logic. Because it uses so few parameters, it is a primary choice for on-device applications. If you need to run predictive forecasting on a smartwatch or a remote industrial sensor, the RNN is compact enough to work without draining the battery. It remains the simplest, most stripped-down neural network capable of maintaining an active memory state. The mechanics and context of this architecture are explored deeply in Algorithm 38 of Imran Ahmed's 50 Algorithms Every Programmer Should Know. The story of sequential data continued beyond the plain RNN. To handle longer strings of data without succumbing to the vanishing gradient, the memory cell had to evolve. This schematic shows the evolution, the long short-term memory unit, or LSTM. By adding mathematical gates to the memory line, engineers learned how to protect the hidden state, ensuring that important context survives the journey.